Hello. Hi, everyone. Good evening, everyone. Welcome back to yet another PyData Pune event. As usual, before moving to today's agenda, I would like to take this opportunity to give a brief introduction about PyData and its mission. PyData is a non-profit initiative of NumFOCUS through which they provide a platform to community for sharing and interacting on the grounds of data and associated genres. The Global PyData Network promotes discussion of various practices, new approaches, and emerging technologies for data management, processing, analytics, and visualization. This year, instead of having multiple conferences, PyData is here with one global conference, that is PyData Global, starting from November 11. So if you're interested in attending, kindly visit PyData Global website. Coming to today's agenda for tonight, we are here with a great talk for you titled as Combining the Power of Historical Stock Data, the Wisdom of Crowd, and the Application of Deep Learning in Stock Market Prediction by Louis Owen. Louis is a data science enthusiast who is always hungry for new knowledge. He pursued a mathematics major at one of the top public universities in Indonesia. Currently, he is into natural language processing. He has great experience as an analytics machine learning intern in various field of industries, including OTA, e-commerce, fintech, smart city, and currently he is working as a data science consultant at the World Bank. So without further ado, over to you, Louis.
Hi all, thank you for the introduction, Maya. Okay, so yeah, as it said, in this session I will talk about the deep learning in stock market prediction, and I think let's get just started. So I will talk about my latest conference paper. This paper is presented at the third international conference in data science and its applications, and it will be indexed in the IEEE publication soon. So the title is SEN, Stock Ensemble-Based Neural Network for Stock Market Prediction using Historical Stock Data and Sentiment Analysis, with me, Luis Owen, as the main author, and my lecturer at the University, Ms. Vini Oktariani, as the second author. In this talk, there will be a presentation in the end of the session. So please feel free and throw me any questions during that session. Deep learning knowledge is required to be able to follow this talk smoothly. So, nowadays, almost all of us has at least a social media account. Sometimes we use it to tell us how's our day going on, what are our latest achievements, what topic of discussions that keep buzzing in our head, and felt like it has to be spread to our community in order to get feedback from them. Or it can also be a platform for us and others to discuss or give opinion about a particular topic. Specifically for the stock market related social media, this platform quite reflects the wisdom of crowd theory, which refers to the idea that large groups of people are collectively smarter than individual experts. And what if we can exploit the data provided from social media as an add-ons to our existing stock market prediction model? Wouldn't it be wonderful to get direct opinion from the driver of stock market movement? The answer is yes. Absolutely, we can exploit the power of social media to do the stock market prediction. And fascinatingly, with the rise of deep learning advancement in the last decade, we can further enhance our prediction performance with the help of deep learning. To summarize, what we did is combining the power of historical stock data, the wisdom of crowds, and the advance of deep learning to predict the stock price in the future. So, here's the approach we are taking. We called our framework as SEN, Stock Ensemble-Based Neural Network. Besides of the fancy name, generally our framework is divided into three big parts: sentiment score extraction, historical stock data prediction, and the fusion machine. The input of our framework is both historical stock data and the microblock text data. The output is the predicted stock price in the future time frame. I will run through the architecture twice. First is the overview of the model, and the second will be a more detailed explanation. So, the first part is a sentiment score extraction model, which takes microblock text data as the input. Before going deeper on the explanation of this part of the model, Let's take a look at this text example. How can you analyze this given text to know its polarity or its sentiment score? We can count the number of exclamation mark, the number of caps lock word, match the word with positive and negative dictionary, and many more. We can also transform the given text to latent space to get more semantic meaning of it. Besides analyzing at individual word level, we can also analyze the effect of surrounding words or also the impact of the very first word into the last word. And all of those ideas are then modeled with the sentiment extraction architecture. There are four main building blocks of this part, which has their own unique purpose. The output from each of the building blocks is passed to the stacked ensemble model. Differ with the traditional ensemble, which only take the average value from all of the building block outputs. Here, we exploit the multilayer perceptron or MLP to find the most appropriate weights which will be given to each of the building blocks. Note that this amazing ensemble architecture is inspired from the work of Gozal et al. In SemEval 2017 Task 5 Challenge. And also, please note that the sentiment score extraction model is trained separately in the beginning. The trained model then used to predict the sentiment score from text related to the chosen stock ticker. The second one is the historical stock data prediction. This part takes historical stock data as the input, and long short-term memory, or LSTM, is used as the prediction model. A lot of effort is done on the feature engineering on the input variables. Then, the output from the historical stock prediction part are joined with the sentiment score extracted from the sentiment score extraction model, and then both of them are exploited as the input to the fusion machine. The fusion machine basically is another MLP, which has a role as the prediction head of our overall model. The output of this prediction head is the predicted stock price in the future time frame. Okay, so that's we have seen how the architecture works in high level. We will now run through once again, but with a more detailed explanation. The sentiment score extraction model takes microblock text data as the input. There's some pre-processing need to be done on the text data before it can be used, which will be not mentioned here. So, for the MLP feature driven, there are three types of manually curated features generated for this model. They are stock features, linguistic features, and sentiment lexicon features. And in total, there are 55 manually curated features generated for this model. The second one is MLP simple word embedding, which takes 300-dimensional word vector representation of the text as the input, while CNN and LSTM takes text with the length of 50 as the input, and then use the pre-trained word-to-vec model to map the text into its vector representation. The output from all of the four models are then become the input of the multilayer perceptron that acts as the stacked ensemble model. Finally, sentiment score is extracted from the given text data. Each of those four building blocks has their own unique purpose. MLP feature-driven exploits the manually curated features to predict the sentiment score. MLP simple word embedding aims to extract the information directly from the average word embedding from the given text. CNN aims to extract the local information from a particular text, while LSTM aims to extract the global one. Here, we can see the details of the architecture for both MLP feature-driven and MLP simple word embedding. So, both of them are three hidden layers MLP. We use the Adam optimizer and mean squared error loss function during the training. Maybe you wonder why mean squared error. So, the unique part in the sentiment analysis is the given data has continuous sentiment score, which is annotated by the financial experts. This data is prepared by SemEval 2017 Challenge. It consists of both Twitter and stock tweets data. And it is bounded in the range of -1 until 1, where -1 means very negative and 1 means very positive, and 0 is neutral. Then, this is the architecture of CNN. Basically, this is the first part of the CNN. So the CNN architecture is divided into two parts, namely the feature extraction and the fully connected network. Here, you can see the visualization of the feature extraction network. I will not explain this now in detail. However, if we have still extra time, and if you are interested more into the CNN architecture, we will discuss it later. And here, we can see the architecture details of the fully connected network for CNN. For CNN, we use two hidden layers MLP with 15 nodes in each of them. Again, Adam is used as the optimizer, and mean squared error is used as the loss function. For LSTM, it consists of Gaussian noise layer, which is performed after the input embedding layer, and two LSTM layers with 100 units followed by the dropout layer in each of them. Then it is followed by the fully connected network. After all of the four models has been trained, we exploit the prediction result from those models as the input to the stacked ensemble model. Here, you can see the visualization of the stacked ensemble model. Basically, it is just a one hidden layer MLP with four nodes. And now, we will discuss about the data splitting methodology when training the sentiment score extraction model. The full training data for sentiment score extraction is separated into three parts, namely train 1, validation 1, and test 1 data. Each of the MLP feature-driven, MLP simple word embedding, CNN, and LSTM is trained on the train 1 data using 10-fold cross-validation. Those four train model will be used to predict both validation 1 and test 1 data. Thus, there are four prediction results for each of the validation 1 and test 1 data. Then, two new tables with 5 columns are created, each for validation 1 and test 1 data. Those columns consist of 4 predicted sentiment score from each of the 4 models, along with the ground truth of the sentiment score. The newly created table from validation 1 data will be exploited as the training data for the stacked ensemble model, namely train 2 data. While the newly created table from the test 1 data will be exploited as the validation data for the stacked ensemble model, namely validation 2 data. Okay, let's skip this. Next is the historical stock data prediction, which takes historical stock data as the input. There are 3 groups of features created in the feature engineering phase: basic features, stock indicator features, and additional features. Basic features consist of the simple moving. Basic feature consists of the open, low, high, close of the price, as well as the volume. So the stock indicator features consist of the simple moving average and some other stock indicators. Additional features consist of the date, time, weekday, etc. In total, there are 22 features used for this historical stock data prediction part. Then, the features created are exploited to the LSTM model. Note that the output of the LSTM is still a sequence output, not a single value output. Then, that sequence output from the historical part are joined with the sentiment score extracted from the macrobook text data, and they are exploited as the input to the fusion machine. Again, the fusion machine is only an MLP, multi-layer perceptron, which has a role as the prediction head of our overall model. The output of this prediction head is the predicted stock price in the future time frame. So, since we treat the stock market prediction as the regression problem, mean absolute percentage error, or is the well-known metric can be used. However, this metric does not take into account the direction of the prediction result. Okay, so what is direction? Consider this scenario. Let's say the difference between the actual price in the future time frame and the actual price in the current time frame is positive. Or in other words, the price in the future time frame is higher than the actual price in the current time frame. And also, let's say the difference between the predicted price in the future time frame is lower than the current actual price. Then, in this scenario, we have a different direction between the actual and the predicted one. And mean absolute percentage error cannot capture that scenario. So, to tackle that problem, we propose a novel way to measure the model performance in the stock market prediction task, namely adjusted mean absolute percentage error. Intuitively, this adjusted MAPE will give 2 times more penalty when the predicted price is in the wrong direction, compared to when the predicted price is in the right direction. So, what are the data we are using to train our SEN model? First, we get all of the historical data from all of the 30 listed tickers in Dow Jones Index Average, or DJIA, index during 2019. Then, we perform a segmentation to get the most volatile stock segment. And it turns out that the chosen stock segment from that segmentation phase is a segment which consists only one ticker, that is Boeing ticker. Maybe you wonder why we have to choose the most volatile stock segment. So it's simply because we do the segmentation in order to minimize the scope of study given the limited time and limited API access to extract the microblock text data from stock tweets. And how we choose the most volatile stock segment? First, we perform a hierarchical clustering with dynamic time warping distance matrix. We use the dynamic time warping instead of the usual Euclidean distance because of the dynamic time warping can detect the similar behavior of time series data better than the usual Euclidean one. So we perform the clustering on all of the 30 listed tickers in DJIA, and after we got several segments, we use two metrics to identify which one is the most volatile segment. We use standard deviation and adjusted volatility. Adjusted volatility is our own defined matrix, which basically measures the mean of the average opening price difference along the time across all stock tickers in that particular segment. So in the mathematical language, this is the formula. For the results, this table shows us the performance comparison measured by MAPE and AMAPE between the model that only exploit the historical stock data as the input and our proposed SEN model, which takes both historical stock data and microblock text data as the input to predict the stock price. We can clearly see there is around 25% reduction of average AMAPE, followed by the large decrease of the standard deviation, that is around 50%. The reduction of average AMAPE shows that SEN succeeded to push down the prediction error, which means that exploiting sentiment score as the additional input to the model succeed to enhance the stock market prediction performance. While the large reduction of the standard deviation also shows that SEN is more confident in doing a prediction compared to the model which exploits only historical stock data as its input. And from the formula of MAPE and AMAPE, we can conclude that value of AMAPE divided by MAPE is bounded in the range of 0.5 until 1, where the infimum, the 0.5, will be reached when all of the data points are predicted in the right direction, and the supremum, 1, will be reached in the other way around. Our results shows that the ratio between AMAPE and MAPE for both historical stock data and SEN model is around 0.75. This means that both of them has a quite good performance in direction-wise. This could be due to our proposed model has a good performance with not many data points are predicted in the wrong direction. On the other side, if the prediction model has a bad performance in direction-wise, then the value of AMAPE will be closer to the MAPE value. So, the key takeaways from this presentation is we succeed to combine the historical stock data, the wisdom of crowds, and deep learning to predict stock price by using our SEN architecture. We also propose a new metric for stock market prediction, namely adjusted mean absolute percentage error, which also take into account the direction of the prediction results. And last but not least, you can check the code implementation here in my GitHub. Thank you for your attention, and please feel free to ask me if you have any questions. Okay, I think that's all for the presentation.
Yeah. So there is a question, Louis, and this is time series is involved along an ensemble model. So, like how you are using time series thing, or how you are keeping track of it.
Oh, so in the ensemble model, it's not a time series model. So it's actually the part of the sentiment score, sentiment extraction model. So it's not a time series. It's not a time series problem because the input is the text and the task is to predict the sentiment score. No temporal aspect there.
Okay. Um, so let's wait for few more minutes if we have more questions.
Okay, cool. I saw a question here. Please cover data sources for the MIPE data. Yeah, so For the historical stock data, I use a package called the Yahoo Finance. So Yahoo Finance Scrape. So yeah, I get the data from the Yahoo Finance.
Okay, we have couple of questions here. Text blob to get the sentiments.
Can we use text block to get sentiments? Uh, can you please elaborate what do you mean by text block?
Okay, so meanwhile, meanwhile the person is typing, let's take another question. Do we
Okay.
have stock with API for Indian stock market?
For that, I'm not quite sure, but I think you can use my code and just try it in for the Indian stock market. But I'm not quite sure about that because I haven't tested it yet.
And there's one more question. Could you please elaborate on the clustering of stocks using a new metric instead of Euclidean distance, please?
Oh yeah. So I'm using the dynamic time warping. Actually, it's not a new metric, and it does so. The benefit of using that metric is we can also measure distance between two time series, not in the same time. So because in time series we can have a similar behavior, but in the different time frame, right? And using that dynamic time warping, we can capture that similarity as well. If we use the Euclidean distance, we only measure the similarity in the same time frame for each of the time frame. You can uh, you can read more about dynamic time warping. Yeah, you can read more about it.
Okay. Uh, so there's one more question. Why shouldn't we use simple time series classification time series? But yeah, why shouldn't we use simple
Uh,
classification?
so the so the aim of my the aim of this research is to predict the stock price in the future. And yeah, I think it's not a classification, but it's a regression task.
And how you are extracting this sentiment data from Twitter or something similar?
Yeah, so as for the training data, I use the data provided by the SEMAFAL 2017. The source is from Twitter and stock tweets. While for the inference for the prediction part, I only use data from stock tweets.
Okay.
Yeah.
So there's one more question. Whether OHLCV is the only data for the forecasting? Can we use any another data?
Whether OHLCV is the only data for the forecast, can you use any other data? V. Sorry, I don't know what's that acronym stands for.
Okay. For historical data, time series must have been there. So I wonder how time series was not involved in modeling.
Okay. Yeah. So the time series is involved in the historical stock data prediction. And why I say that the sentiments extraction model isn't a time series problem because how it works is just basically take the text a text and then output a sentiment score. And then the sentiment score is joined with the time series data. So yeah, so the sentiment score is joined with the sentiment with the historical stock data, and then the combination of those two sources will be become the input to the fusion machine. Yeah.
So another question is, are we taking after our market demand into consideration?
Yeah. So actually, this research is done before all of the situation. So yeah, I think it will not works using this kind of situation, and we have to train it again. Yeah, but it's quite a volatile situation right now.
Okay. Can we use CNN instead of DTW for time series pattern recognition?
Can we use CNN instead of DTW? Hmm, I think it's worth to try. Yeah, it's interesting, but yeah, I haven't tested yet, but I think it can. But the purpose of I'm using the DTW is to segment the stock market. Yeah. So yeah, I think we can. I think it's interesting to use CNN also.
Okay. So, what kind of exploratory data analysis can we perform on the text, or you are performing on the text?
Yeah. So actually, the main parts of the EDA I did on the text data is like to decide what kind of pre-processing I need to perform in the text data. Like, is it do I need to remove the stop words, or when should I remove the stop words? Yeah. So the pre-processing is different for each kind of the model. Like for the MLP field driven and for the MLP symbol embedding, the kind of pre-processing is different from each other. So the EDA is did for that.
Okay. So, we have we have the full forms for the word OHLCV. So, before that, let me read the question again. So whether OHLCV is the only data for forecasting, can we use any another data? And here by O means open, H for high, L for low, C for close,
Oh, okay,
V for void.
okay. Yeah, actually, I'm not only using the OHLC and V. Actually, I also use like the date, the time. Is it a weekday? Actually, yeah, it's not is it a weekday, but is it a Monday, Tuesday, Wednesday, and something like that. Yeah. So for like in the historical stock data part, I think I use around 22 features, not only the OHLC and V,
Okay.
and also the stock indicators, as I said before. Like I'm using the simple moving average, the Bollinger indicator, yeah, and some other stock indicator.
So there's another question which is related to production, like productionizing the model. So does model need to be retrained every time step? If so, do we require GPU in production?
Uh, I think it's once it is trained, I think it can be used for the inference. But yeah, this until now I haven't thought about the production phase because yeah, it is only for the research part, and its GPU is better because during the training phase I also use GPU in Google Colab.
Okay, and okay, so there's one more question. Like we have couple of questions. Is fundamental analysis of any particular company also involved in your prediction?
No, haven't. I haven't used that. I haven't take into account that part. So I'm only using the social media data and the historical stock data.
Okay. Another question, which is again related to scalability. How scalable the model is? Can we track 100 stocks?
Up to now, it's not that scalable yet, since it is only in one ticker, the Boeing ticker. Again, it's because of the API limit. But if we have more, if I have more time back then, I think I will train it for the broader range, not only for one Boeing ticker. But
Okay.
the interesting part is the methodology. Yeah. the methodology of this research.
Yeah. So another question is weather is the only data for forecasting. Can we use any another data?
I think it's same like the question before. It's the OXLPV, isn't it?
Yeah.
Yeah.
Moving on to next one. How are you penalizing the model for wrong directions?
Uh, I'm using the loss function. So the loss function I use is the mean squared error. So if the yeah, so during the training, I still use the mean squared error, but as for the metric, I use the adjusted mean absolute percentage error, which we propose. And using that metric, we can also take into account the wrong direction prediction.
Okay. So there is one more question, which is, do you think that sample size is enough for 22 features?
Example says, yeah, I think it's enough because for the historical stock data, it's a 1 hour lag data, and it's all around the year, so it's quite much data. And 22 is not that much, as for my opinion.
Yeah. And before moving on to the last question, which I think is a bit personal to you, so if you can reiterate through the architecture of the model, just that one slide wherein you have the model, the ensemble one kind of thing.
Okay, this one.
Yeah. Uh, and Louis, there is one more slide wherein you have like description of these things. So, can we read it somewhere? Like, can we read the details somewhere? Do we have details somewhere?
Oh, so actually the paper is not published yet, but you can found the description in the GitHub. I also write the description about the
Cool.
model. Yeah,
Okay.
and I think I will share my GitHub here. So yeah, here.
Okay. I'll post it in the description of the video. So if anyone want to have a broader look or want to see the details, then can go through the GitHub link.
Yeah.
So yeah,
Once the paper is published, I will also put the link to the paper there.
sure. And moving on to the last question. So are you using your model, to personally invest in share market?
Uh, Personally, I'm not sure yet because yeah, again the training data is still limited, but and then it's also for the international stock, right? It's not in like my local index. Yeah, so I'm not. I still haven't think about to invest with my own model.
Yeah. So I think we do not have more questions. So let's wrap it up. Lois, we are very grateful to you for sharing your time,
Yeah,
and we had good questions and answers coming from our audience as well as from your side. Thanks a lot, everyone, for joining. And this talk will remain on YouTube. So if anyone want to rewatch the video, then they can watch immediately after we'll stop the live stream. So thank you once again, and hopefully we'll connect you soon.
Okay.
Thank you.
Thank you also for inviting me. Hope this session will be beneficial for you all.
Sure, sure. Thank you, Luis.